And now we are starting with a new problem on the design of singly reinforced beam. The singly reinforced beam has been given to us, which we need to design, and the working dead load is 25 kilonewton per meter inclusive of self weight. This is the parameter which has been given. Now working dead load. Now there are two types of loads. One is working load and one is ultimate load. Now working, normal or service load are one and the same. Working load or normal load or service load, these terms are interchangeable for one another. The difference between a working load and ultimate load is that ultimate load has the load factor, partial safety load factor is already applied to it. Okay, so when the load factor is already applied, it becomes ultimate load. Now in this case it is not ultimate load. What we have been given is working dead load of 25 kilonewton per meter inclusive of self weight. Now what is a dead load? Now dead load is the self weight of the beam, the self weight of the slab. From the slab the load goes on the beam, or it could be the wall which is giving the load on the beam. The beam is supporting that particular wall. So all these are the dead loads. All these dead loads have been compiled together, calculated together, and they have given us the value as 25 kilonewton per meter. And they have told us that there is a live load of 20 kilonewton per meter. Now live load is anything which is movable. Over there could be the human beings which are moving, or maybe the furniture and things like that. So live load on that particular beam is coming to 20 kilonewton per meter. Now look at this. 25 kilonewton per meter is the working dead load, and 20 kilonewton per meter is the live load. Now when we have the unit kilonewton per meter, it means that it is a UDL. So dead load is also UDL, the live load is also the UDL. Now let us have a look at the further part of the problem. Take D by B ratio, the effective depth to the width of the beam as 2.5:1, and design the beam using M25 grade concrete and Fe 500 grade steel. Effective span of the simply supported beam is given to be 5 meters. They have also asked us to give a check for deflection. As mentioned earlier, in this chapter we are looking at design only for flexure. We are not taking into account the design for shear, torsion and other things. But sometimes the serviceability check may be required. So at that time we will be giving the serviceability check. Something like over here what they have asked us is give the check for deflection. So that is a serviceability check. Now also notice another thing, the beam is a simply supported beam. Its effective span is already calculated and told to us to be 5 meters. We have been also told that there is UDL in the form of dead load, in the form of live load. And please note, when it is not mentioned on how much portion the UDL is, we assume that it is over the full span. So UDLs are expected to be appearing or applied on the full span. So let us go ahead with the solution. The data, the imposed the load which is coming on the beam in terms of dead load is 25 kilonewton per meter, that is with the self weight, and the W with the live load is 20 kilonewton per meter. It's a simply supported span, simply supported beam with effective span as 5 meters. Parameters are M25 concrete and Fe 500 steel. The effective depth to the width ratio is 2.5:1. We have been asked to find the effective width, the effective depth, the AST, that is the area of steel, number of bars, and give the check for deflection. Note one thing over here, we are finding B and D, but we are not finding the capital D over here. We are not finding the overall depth over here. Please note that overall depth is required to find the self weight of the beam. Any other calculation, the overall depth does not feature. We don't require the overall depth at all. We require the overall depth only to find the self weight, but over here, since the dead load or since the load is given inclusive of the self weight, the parameter overall depth is not necessary. We need only effective depth for all the calculations. Another place where we use the overall depth is only when we draw the graphical view of the beam. Over there we give the overall depth, what is the depth of the beam. So let us start with the calculations. Step 1, grade of concrete and steel. we need to assume this if it is not given. Now in this case we are happy it has been given, both the parameters M25 concrete and Fe500 steel, both have been given. Now step 2, since the width of the beam is not given, let us assume the width of the beam to be 250 mm. 250 mm. Now they have told us to take the depth of the beam, effective depth of the beam, to the width ratio as 2.5:1. So D upon B is 2.5. So D upon 250 is 2.5. So D becomes 2.5 into 250, that is after cross multiplying. So D becomes equal to 625. We normally round it off to about 50 mm on the higher side. It does not mean that we have to go maximum up to 50. It can be anywhere from 0 to 50 that we can round it off. Now over here we take this 50 mm and then this D can be taken safely as 665 mm. So as I mentioned, we round it off to maximum value of 50 mm. I could also take D as 650, that is this 625 plus 25 I could take, and then D I could take 650. But in this case we have taken the value of D as 675 and then we proceed. Now the next step is to find the bending moment acting on the beam due to all the loads, that is the dead load and the live load. Calculate the value of bending moment ultimate by applying the partial load factors. Now what is the total UDL per meter of the span? Now total UDL will be UDL due to dead load plus UDL due to live load. So 25 plus 20, so total UDL is 45 kilonewton per meter. Now since it is a simply supported beam with UDL, the maximum bending moment which occurs at the mid span is given by WL squared by 8. W total due to dead load as well as live load is 45. L, the effective span, is given as 5, so that becomes 5 square upon 8, or the bending moment, the external acting bending moment in the working condition, in the normal condition or the service condition, the bending moment is equal to 140.625 kilonewton meter. Now what is the ultimate bending moment coming on the beam? The ultimate bending moment is load factor partial safety factor multiplied by the bending moment, that is 1.5, which we have already seen before. So ultimate bending moment which is going to come on the beam is 1.5 into 140.625, or the ultimate bending moment is 210.94 kilonewton meter. So the ultimate bending moment coming on the beam due to the dead load and live load acting on the beam is 210.94 kilonewton meter. Now let us look at the next step over here. The next step is calculate the value of MU limiting, the maximum value of bending moment it can resist, the maximum value of bending moment it can take safely without showing signs of failure. So we are calculating MU limiting of the beam. So for that we are using IS 456 clause G 1.1c on page 96, that is this one. MU limiting is equal to 0.36 XU max by D into 1 minus 0.42 XU max by D BD square FCK. Now since it is Fe500, we have XU max by D as 0.46. So using XU max by D as 0.46, let us calculate. So this comes as 0.36, 0.46, 1 comes down as it is, then minus 0.42, this is 0.46 into width is 250, depth is, effective depth is 675, and FCK is 25. So MU limiting comes to 381.33 into 10 raised to 6 Newton mm, or MU limiting comes to 381.33 kilonewton meter. We have already seen the calculation earlier that from Newton mm to kilonewton meter, what happens is we have to divide by 10 raised to 6. So MU limiting comes to 381.33 kilonewton meter. How much is the bending moment coming on the beam? Ultimate bending moment coming on the beam is 210.94 kilonewton meter. How much can it resist? Ultimate 381.33 kilonewton meter. So if MU limiting 381.33 is greater than bending moment which is going to come on it, that is 210.94, the assumed section, whatever dimensions we have taken, that is B and small d, that is effective depth, that is acceptable. Now since the mu limiting is greater than bending moment which is coming on the beam, we know that the design is an under reinforced section. Now since it is under reinforced section, we can find the value of AST by using IS 456 clause G1.1b on page 96 by using this equation, with the only change that this mu will be put equal to bending moment which is coming on the beam. For the bending moment which is coming in the beam, if you equate it to mu, we can find the value of AST. So mu becomes 210.94 into 10 raised to 6 will be equal to 0.87. Fy is 500. AST we are trying to find out. D is 675. 1 minus AST. Fy is 500. B is 250. D is 675. FCK is 25. Now when we solve this equation, please note there is AST over here, there is AST over here. This becomes a quadratic equation. Many of our calculators allow us to directly solve the quadratic equation and gives the value, positive as well as negative value of the variable. But wherever it is not possible, we have to use the formula of the quadratic equation to solve the quadratic equation and get the roots. So finally solving it, we get the value of AST as 792.90 mm square. So solving this, we come to know that the steel required for a moment of 210.94 into 10 raised to 6 Newton mm for a moment equal to this much, that is ultimate moment, is 792.90 mm square. Now having got this, we have to give the check for minimum steel. So minimum steel to be provided in the beam, it is given in the clause 26.5.1 page 46-47 in the code IS 456 2000. So AS upon BD equal to 0.85 upon Fy. So we are using that AS upon BD equal to 0.85 Fy. So cross multiplying this BD goes on top. So AS becomes equal to 0.85 into BD upon Fy. So 0.85, B is 250, effective depth is 675, Fy is 500. I think there is a mistake over here. Fy is 500, so we get AS as 286.88. Now this value, look at this value, this is much lesser than this, so we are going to use this value. So since this value, calculated steel, is much more than this, provide 792.90 mm square. Now when we are going to provide this much, how many bars are required? So assume the diameter of the reinforcement. In order to calculate the number of bars to be provided, we assume the bar diameter to be 16 mm. 16 mm diameter bars we are going to use. What is the area of one bar? Area of one bar is given by A is equal to pi d square by 4. So A is equal to pi by 4 into 16 square, or area of one bar is 201 mm square. So how many bars will be required? Total area required is 792.90. One bar is 201. So total area divided by area of one bar gives me 792.90 divided by 201 gives me 3.944, say 4 bars. That means provide 4 bars of 16 mm diameter for that particular beam. So in order to take care of this, we have to provide 4 bars of 16 mm diameter. The next check which is required to be done is additional requirement, give the check for deflection. Now the check for deflection is given in IS 456 2000 clause 23.2.1 page 37. What does it say? The vertical deflection limits may be generally assumed to be satisfied. The vertical deflection will be satisfactory provided that the span to the depth ratios are not greater than the values which have been given over here. So span to depth ratio for a simply supported beam cannot be more than 20. That is what exactly the code says. The vertical deflection limits means the vertical deflection will be assumed to be satisfied provided that the span, that is the effective span, to the depth ratio, to the effective depth ratio, span upon effective depth is not greater than, for simply supported beam, 20. So for simply supported beam, span to effective depth should be less than 20, should not be greater than 20, means should be less than 20. So 5000 divided by 675 should be less than 20. Yes, this calculation tells us that it is 7.407 and it is less than 20. So from deflection point of view, this beam is safe. It will not deflect more than the permissible value. Having done this, having got this done, we have completed the flexural part of the design. Let us see how it appears in the sketch. We have the effective span somewhere over here as 5 meters. At the bottom, we have provided the steel, which is 4 bars of 16. At the top, we have over here something called as the hanger bars. Hanger bars. They allow us to keep these bars in position. So let us have a look at the cross section. The cross section appears here. The 4 bars of 16 are here provided. 2 hanger bars are provided over here. Let me tell you what exactly is the purpose of these 2 hanger bars. Now these 2 hanger bars will have a round bar going in the periphery like this, and these bars, these 4 bars will be sitting on the round bar. A bar which will be going around, all round this. So these bars will be sitting on that. So these bars make this one, this round, all round bar, and it makes these bars, this AST, hang over this portion. Now notice this portion over here, from the bottom of this to here, is the clear cover. If we don't provide this as a round, all round bar over here and suspend this, obviously these 4 bars will be lying down over here. Giving the cover would be extremely difficult. So that's why these are called as the hanger bars. So hanger bars are generally those bars which are of very small diameter. They should only permit the people, the workers, to move around whenever concreting is being done, or slab checking is being done, the steel checking is being done, or electrical conduits are being put. So during that time, whenever people are moving over the cage, the reinforcement cage, this should not bend. So 8 mm bars are provided. Some people provide even 6 mm bars. There is no problem. So in this case, what we have done is we have provided 8 mm bars as the hanger bars, and at the bottom we have 4 bars of 16 mm. Also please note over here that all round that bar which will be going is still not drawn over here. It is still not shown over here. But when we will be taking the shear design, at that time we will be discussing about the design aspects of that and how it is provided also. So we will be coming to that bar, the bar which is called as the stirrup, later. So over here the main steel is 4 bars of 16 mm diameter. Please note how 4 bars of 16 are depicted over here. Since it is a high yield strength bar, the symbol TOR is shown over there. Please notice the symbol TOR. Now the symbol TOR is T, O and R. So TOR is written over here. So this is always the number of bars. This is the symbol for high strength, high yield strength bars, and that's the diameter. Same thing over here, 2 number of bars. TOR steel is used, 8 mm bars, 8 mm is the diameter. So that's how we depict. And in the cross section, whenever we are showing any bar in the cross section, please note, for individual bars, if we are showing, we put a circle and then mark it outside. And if it is collective, either we use a circle or an ellipse and then show it outside. Just look at the cross section, how it has been given. As far as the main beam is concerned, we can either write the numbers next to the bar, or we can show an arrow also. We can show an arrow to showing which particular component it represents. So that's the way we represent graphically the beam.